Hello, the purpose of this lecture is to give more examples of regular surfaces. So we'll be basically studying surface of regular revolution first. So what is surface of revolution? So suppose you take a planar curve and let us take a straight line which does not intersect that planar curve, and you rotate that curve around that straight line. So we'll get a surface depending on that curve is nice one. Okay, so let us begin. Yeah, so let us take a curve in uh, XZ plane. Okay, so what we are going to do is the following. So this is my x-axis, this is y-axis, this is z-axis. So let us take a curve in this xz plane. Okay, and let us take this curve to be simple. Means that it does not self-intersect other than the endpoints. And then, so you rotate this curve around the z-axis. Okay, so you will get a surface corresponding to this. Okay. So suppose I take that curve to be regular simple curve. So then the surface of revolution, it will be a regular surface. So that we are going to show. So let alpha be equal to fb comma 0 gb, where this b, it belongs to some interval be a regular curve in xz plane. Okay, so also assume that this alpha is simple. So assume alpha is simple. So that is, so if I restrict this alpha uh, to the interior of I, so then it is an injective map. Okay. And also assume, so this curve is disjoint with this z-axis. So assume, so this fp is greater than 0. Okay. So this will imply that, so alpha does not intersect z-axis. Okay. So now let us take S to be the following. So S is given to be fb cos u, comma fb sin u, comma gb, where this b, it belongs to the interval I, and u is running from 0 to 2 pi. Okay. So S is called the surface of revolution, so obtained by revolving alpha around z-axis. Okay. So our next claim is, so this surface, it's a regular surface. So S is a regular surface. Okay. So how to show that this surface is a regular surface? If I take any point, I have to find a regular surface patch containing that point. Okay. So you have to cover this surface with regular surface patches. Okay. So now let us take this map. So let sigma ub to be equal to fb cos u, comma fb sin u, comma gb. Okay. So now, so this u and b, it belongs to this open set, the interval 0 to pi product with the interior of I. Okay. All right. So let us call this to be equal to capital U, this open set. So U is an open set in R2. Okay. All right. So, so first observe that. So sigma is injective on U. Okay. So sigma is injective on U. So why this is true? So sigma U1 V1 equal to sigma U2 V2. If I take, I have to prove that U1 equal to U2 and V1 equal to V2. So this implies that, so F V1 cos U1 equal to F V2 cos U2, F V V1 sin U1 equal to F V2 sin U2, and G of V1 is equal to G of V2. Okay. So let us take this equation to be 1 and this is to be my 2. So if I take the square of this equation 1 and add with the square of the equation 2, so then what we'll get is the following. So f of v1 square will be equal to f of v2 square. Okay. And also gv1 is equal to gv2. Okay. And this f, we have taken it to be positive, so this will imply that fv1 is equal to fv2. All right. So so this, if I call it to be 3, so this is from 3. So we have this thing. So fb1 equal to fb2, gb1 equal to gb2. So from here, so this curve, so alpha is simple. So alpha is simple. So this will imply that so alpha, if alpha b1 is equal to alpha b2, so then b1 equal to b2. So here, because fb1 is equal to fb2, gb1 equal to gb2, so therefore alpha b1 is equal to alpha b2. So therefore, so alpha b1 equal to alpha b2, so that implies that b1 equal to b2. Okay. And again, from these two equations, so we have shown that fb1 equal to fb2, b1 equal to b2 means fb1 is equal to fb2. Okay, so therefore, so what we have, so cos u1 equal to cos u2, sin u1 equal to sin u2, and both this u1, u2, it belongs to this interval, this open interval, 0 to 2 pi. So this will imply again that this u1 is equal to u2. Okay, so therefore what we have shown that, so therefore this map sigma is injective on u. Okay, and also by the definition of the map of sigma, sigma is also continuous. So sigma is continuous on u. Okay, so now this sigma, it is a map from this u to sigma u. So this is, so I've taken the image of this map. So this is automatically surjective, is surjective. Okay, sigma is injective, surjective. So therefore sigma is a bijection. So sigma inverse exists, and it is a map from sigma u to u. Okay, so the sigma u, it is an open set in S. So sigma u is open in S. It is not open in R3. Note that thing. Okay. So now we have to show that sigma inverse is continuous. So sigma, so claim is sigma inverse is continuous. Okay. So how to show this thing? So we have to apply a trick. So this trick we have applied earlier also. So sigma ub is of this form: xub, yub, zub. Okay, and so xub is equal to fp cos u, yub is equal to fp sin u, and zub is equal to gb. Okay, so let us take this thing, and so the partial derivatives of this x, y, z it exists, and it exists up to a desired order. So whatever order you can take, provided the function f and g are also nice. So I have taken this f alpha to be a regular curve. So f and g are a differentiable curve. Okay. All right. So sigma is differentiable. Okay. So now, so what will be the differential of this sigma at any point? Yeah, so maybe we will not need the differential of the sigma. So sigma is differentiable. And now what you do, so let us take this function. So define a function capital F u cross R to R3. So f of ub comma t, so this is defined to be equal to x ub y ub comma z ub plus t. Okay. So this function f is differentiable as sigma is differentiable. Okay. So now what will be the differential of this map capital F? Okay. So differential, it is a linear operator. So I'll just write the corresponding Jacobian matrix. So it will be the partial derivative of x with respect to u, partial derivative of x with respect to b, then 0, partial derivative of y with respect to u, partial derivative of y with respect to b, 0, and then zu, zb, and so then what we are doing last, we are taking the partial derivative of this with respect to t. So that is equal to 1. Okay. All right. Okay. So f is differentiable. Okay. So what will be the determinant of this matrix? So this will be, so del x, y, del ub. Okay. All right. And similarly, also I can define this thing. So similarly, so suppose if gxy z is x ub y ub plus t comma z ub. Okay. So determinant of, sorry, so this will be your u comma b comma t. So determinant of the differential of this will be equal to del xz del u b. Okay. And if h is defined in this way, x ub plus t comma y ub comma z ub. So then determinant of the differential of this map, so this will be equal to del yz del ub. Okay. All right. So what is the purpose of doing this thing? So now, like again, let us take this sigma ub. Okay, so which is defined to be equal to, so f b cos u, f b sin u, comma g of p. Yeah, all right. Okay. So now let us compute this del xy del ub. So this is my xub, this is my yub, and this is my zub. Okay. So if I compute this del x y del ub, which is nothing but determinant of xu, yu, xb, yb. Okay, so if I compute this thing, so this will come out to be equal to minus 2 times fb times f prime b. Okay, and so what will be my del yz del ub? So this you can compute it to be equal to, so g prime b fb cos u, and del xz del ub, so this is equal to g prime b fb sin u. Okay. Okay, all right. So now the claim is, so one of this will be not equal to 0. Okay. So one of this is not equal to 0. Okay, so how do you show this thing? So suppose all of them are equal to 0. So then what you'll get? So if all of them are 0, so then, so this fp times f prime b is equal to 0. G prime b fb cos u is equal to 0, and g prime b fb sin u is equal to 0. Okay, so fp is greater than 0, so this will imply that f prime b is equal to 0. And from this two equations, so what we'll get? So g prime b square fp square is equal to 0. So this will again tell you, because f prime b, fp is greater than 0, this will tell you that g prime b is equal to 0. So this implies that if I take this alpha prime b, so this is equal to f prime b comma g prime b, which is equal to this 0 vector. Okay, so this is a contradiction. This is a contradiction as alpha is regular. Okay, so alpha prime b is not equal to 0 for all b. Okay, so therefore, so this claim is true. So therefore, this is true. Okay, so one of this is not equal to 0. So let us assume. So let us assume first del xy del ub is not equal to 0. Okay. Okay. So again, if I go to the definition of this capital F, so determinant of this differential, so this is not equal to 0. So determinant of this differential of F, so this is not equal to 0. And recall that this F, it is a map from this U cross R2, R3. Okay. So again, so this implies that, so this implies the following. So let us take the point UB, comma 0. All right. So there exists and okay, so this follows from inverse function theorem. So by inverse function theorem, so there exists an open set U1 contained in this U and a number and epsilon greater than 0 such that, so this point U comma B comma 0 is contained in U1 cross minus epsilon to epsilon. Okay. And so F restricted to this open set is a diffeomorphism. So that is, so F restricted to this thing is differentiable. So this is differentiable and inverse of this map is also differentiable. So this and inverse of this map is differentiable. Okay. So let me draw a picture. So this is my, say, U1, which contains the point UB, comma 0. And now you are taking this open set. So the whole thing is U1 cross minus epsilon to epsilon. And this map F, it takes this open set to another open set in R3. So this is my, say, surface. Okay, so this F of U1, it will be something here like this. And F of this E1 cross that interval minus epsilon to epsilon, this will be something like this. So this is F of E1 cross minus epsilon to epsilon. Okay, and this is my point f u b comma 0. Okay, so this inverse of f is applied on this open set, applied on this open set. Okay, and so what more you have? So sigma inverse is exactly equal to, so sigma inverse, so restricted to this sigma of u1 is exactly equal to the f inverse restricted to so restricted to again sigma u1. Okay, so this implies sigma inverse is differentiable as f inverse is differentiable. Yeah, so this is my also sigma of u1. Okay, so we have two maps, sigma inverse so sigma inverse will be equal to f inverse. Yeah. Okay, so therefore yeah, so one thing, so instead of differentiable I should write here sigma inverse is continuous as f inverse is continuous. Okay, so sigma inverse restricted to this sigma of u1 is equal to f inverse sigma u1. So sigma inverse is continuous because f inverse is continuous. Because f inverse, it is a differentiable map, and in particular, it will be a continuous map. So therefore, sigma inverse will be continuous. So that is the thing we need. So this implies, so sigma is a homeomorphism onto okay, so sigma restricted to u1 is a homeomorphism onto its image. So that thing we have shown. So therefore, if I take this u1 comma sigma restricted to u1, so this is a regular surface patch. Okay, so this is a regular surface patch corresponding to the point ub. Okay, so now if I take any other point u prime b prime, they can get another surface patch. Okay, so another thing, let me say this thing. So here we have assumed the this del x, why del ub not equal to 0. And if del yz, del ub not equal to 0, so then we work with, so we work with this map. Work with this H map. So determinant of differential of H, so that will be not equal to 0. and we'll get the similar thing. So then we work with the map H and get the regular surface patch. And if so del xz del ub is not equal to 0, so then we work with the map capital G and get the regular surface patch. Okay, so therefore what we have shown that this S, so this is a regular surface. So now let us take one particular example. So torus, how do you get a torus? So you take this 3-dimension space and you take a circle like this, whose center it lies on the x-axis. And let us take the radius of the circle to be r. Okay, and now what you do, so you rotate this around z-axis. Okay, uh, so here, so we have taken this a minus r is, let us take it to be some positive number. Okay, so and you are rotating this circle around z-axis. Okay, so you'll get a surface of revolution. So this is has been rotated like this. Okay, so that is called your torus. Okay, so you'll get a picture like this. Yeah, so this is my torus as a surface of revolution. Okay, so so what I'm doing here, let me write. So torus, uh, so this, so what is my curve alpha b? So if b, it will be a plus r cos b, comma 0 r sine b. Okay, and this a minus r is greater than some positive number. So this I have taken. So this torus, it will be a plus r cos b, comma cos u, a plus r cos b, comma sine u, then r sine b. Okay, so this u, it is varying from 0 to 2 pi. Okay, and this b, it is again, it is varying from 0 to 2 pi. So if I take this thing, so this t is called torus. Okay, so this torus is a regular surface. Okay, so this torus, it is a regular surface. Okay, so now let me give a few more examples. So torus, uh, minus disks. So what does it mean? So you have shown that this torus, so this is a regular surface. Okay, and now you take and take a subset of this torus. So this is my torus. So take this surface, so such that this is homeomorphic to, so this region, so this region R, let us call it to be R. So R is homeomorphic to an unit disk in R2. Okay, and now let us take, so let us take this S to be equal to torus minus this R. Okay, all right, so you're removing a closed disk from the torus. So what picture you will get? So what will be my S? So S will be something like this. So after the removal, so you'll get something like this. Okay, all right. And if I remove just the interior of R, so if I take S bar to be equal to torus minus interior, just the interior of R, so then you'll get a boundary. Okay, so this is called boundary of the torus, and this whole kind of thing, so this is called genus. Okay, so now you take this S bar. So this is a genus one surface with one boundary component. And let us take, so suppose this is in R3. It is lying very nicely. And let us take a reflection of this thing around this XZ plane. So if I take this thing, so I'll get another copy of this. Same copy of this, but it will be reflected. Okay. Let me draw again. Yeah, so I have this two copy. Okay, so here let us call this boundary to be equal to C1 and this to be my C2. Okay, so in R3, so C1 and C2 have same length. So C1 and C2 have same length. Okay, and now what you do, so you translate this C1 to C2 by an isometry. Okay, so in other words, so you are gluing these two surfaces along the curve C1 and C2. So you just glue this thing, so you'll get another surface. So now you'll get these two holes, so two genus, and here you have the attachment. So this gluing, it has been taken over here. So we'll get another surface in R3. Okay, so this is genus 2 surface in R3, okay, without any boundary. Okay, so this surface, let us call it to be S2. S2 is equal to this genus 2 surface in R3 without any boundary. So S2 is a regular surface, and this algorithm you can continue. So again, you can take a puncture on this, or not puncture, you can remove an open disk from S2. So again, if I take this S2 minus some interior of this R, meaning, so suppose again, if I take this genus 2 surface, and if I again remove this thing, so this is my R, so take the interior of R and remove it from S2. So what I'll get? So I'll get a surface of genus 2 with one boundary component. Okay, and let us take this surface with one boundary component interior of R. Let us call it R prime. So that will be equal to this. Maybe I'll draw it here. And again, I can put a metric on these two surfaces with boundary component such that length of C1 is equal to length of C2. And then what you do, so you glue along this C1 and C2. Okay, so you'll get a surface of genus 3 which does not have any boundary. Okay, so this is S3. So it is a genus 3 surface without boundary. Okay, so for any g greater than equal to 0, Sg is a regular surface in R3. Okay, so what is S of 0? So S of 0 is sphere. S of 1 is just the torus. And S2 is this genus 2 surface. And you continue like this. Okay, so Sg is my this genus G surface. Okay, so all these are my regular surfaces in R3. Okay, so I'll stop here.